Chapter 4. Simplest Cases. Now let us see how, on first principles, we can differentiate some simple algebraic expression. Case 1. Let us begin with the simple expression y is equal to x squared. Now remember that the fundamental notion about the calculus is the idea of growing. Mathematicians call it varying. Now as y and x squared are equal to one another, it is clear that if x grows, x squared will also grow, and if x squared grows, then y will also grow. What we have got to find out is the proportion between the growing of y and the growing of x. In other words, our task is to find out the ratio between dy and dx, or, in brief, to find the value of dy by dx. Let x then grow a little bit bigger and become x plus dx. Similarly, y will grow a bit bigger and will become y plus dy. Then, clearly, it will still be true that the enlarged y will be equal to the square of the enlarged x. Writing this down, we have y plus dy is equal to x plus dx squared. Doing the squaring, we get y plus dy is equal to x squared plus 2x times dx plus dx squared. What does dx squared mean? Remember that dx meant a little bit of x. Then dx squared will mean a little bit of x. That is, as explained above, it is a small quantity of the second order of smallness. It may therefore be discarded as quite inconsiderable in comparison with the other terms. Leaving it out, we then have y plus dy is equal to x squared plus 2x times dx. Now y is equal to x squared, so let us subtract this from the equation, and we have left dy is equal to 2x times dx. Dividing across by dx, we find dy by dx is equal to 2x. Now this is what we set out to find. The ratio of the growing of y to the growing of x is, in this case before us, found to be 2x. Note, this ratio dy by dx is the result of differentiating y with respect to x. Differentiating means finding the differential coefficient. Suppose we had some other function of x, as for example u is equal to 7x squared plus 3. Then, if we were told to differentiate this with respect to x, we should have to find du by dx, or what is the same thing, d 7x squared plus 3 over dx. On the other hand, we may have a case in which time was the independent variable, such as this, y is equal to b plus half at squared. Then, if we were told to differentiate it, that means we must find its differential coefficient with respect to t, so that then our business would be to try to find dy by dt. That is, to find db plus half at squared over dt. Numerical example. Suppose x is equal to 100 and therefore y is equal to 10,000. Then, let x grow till it becomes 101. That is, let dx equal to 1. Then the enlarged y will be 101 times 101, which is equal to 10,201. But if we agree that we may ignore small quantities of the second order, 1 may be rejected as compared with 10,000. So, we may round off the enlarged y to 10,200. Y has grown from 10,000 to 10,200. The bit added on is dy, which is therefore 200. dy by dx is equal to 200 over 1, which is equal to 200. According to the algebra working of the previous paragraph, we find dy by dx is equal to 2x, and so it is for x is equal to 100 and 2x is equal to 200. But you will say, we neglected a whole unit. Well, try again making dx a still smaller bit. Try dx is equal to 1 over 10. Then x plus dx is equal to 100.1. and x plus dx squared is equal to 100.1 times 100.1, which is equal to 10,020.01. Now the last figure 1 is only 1/1,000,000th part of the 10,000 and is utterly negligible. So we may take 10,020 without the little decimal at the end, and this makes dy equal to 20, and dy by dx is equal to 20 over 0.1, which is equal to 200, which is still the same as 2x. Case 2. Try differentiating y equal to x cubed in the same way. We let y grow to y plus dy, while x grows to x plus dx. Then we have y plus dy is equal to x plus dx cubed. Doing the cubing, we obtain y plus dy is equal to x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed. Now we know that we may neglect small quantities of the second and third orders, since when dy and dx are both made indefinitely small, dx squared and dx cubed will become indefinitely smaller by comparison. So regarding them as negligible, we have left y plus dy is equal to x cubed plus 3x squared times dx. But y is equal to x cubed, and subtracting this, we have dy is equal to 3x squared times dx, and dy over dx is equal to 3x squared. Case 3. Try differentiating y is equal to x to the power 4. Starting as before by letting both y and x grow a bit, we have y plus dy is equal to x plus dx to the power 4. Working out the raising to the fourth power, we get y plus dy is equal to x to the power 4 plus 4x cubed times dx plus 6x squared times dx squared plus 4x times dx cubed plus dx to the power 4. Then striking out the terms containing all the higher powers of dx as being negligible by comparison, we have y plus dy is equal to x to the power 4 plus 4x cubed times dx. Subtracting the original y is equal to x to the power 4, we have left dy is equal to 4x cubed times dx, and dy by dx is equal to 4x cubed. Now all these cases are quite easy. Let us collect the results to see if we can infer any general rule. Put them in two columns, the values of y in one and the corresponding values found for dy by dx in the other. Thus, the table shown below. Just look at these results. The operation of differentiating appears to have had the effect of diminishing the power of x by 1. And at the same time multiplying by a number, the same number in fact, which originally appeared as the power. Now, when we have once seen this, we might easily conjecture how the others will run. You would expect that differentiating x to the power 5 would give 5x to the power 4, or differentiating x to the power 6 would give 6x to the power 5. If you hesitate, try one of these and see whether the conjecture comes right. Try y is equal to x to the power 5. Then y plus dy is equal to x plus dx to the power 5, which is equal to x to the power 5 plus 5x to the power 4 times dx plus 10x cubed times dx squared plus 10x squared times dx cubed plus 5x times dx to the power 4 plus dx to the power 5. Neglecting all of the terms containing small quantities of the higher orders, we have left y plus dy is equal to x to the power 5 plus 5x to the power 4 times dx. And subtracting, y is equal to x to the power 5 leaves us dy is equal to 5x to the power 4 times dx, whence dy over dx is equal to 5x to the power 4, exactly as we supposed. Following out logically our observation, we should conclude that if we want to deal with any higher power, call it n, we could tackle it in the same way. Let y equal to x to the power n. Then we should expect to find that dy by dx is equal to nx to the power n minus 1. For example, let n equal to 8. Then y is equal to x to the power 8, and differentiating it would give dy by dx is equal to 8x to the power 7. And indeed, the rule that differentiating x to the power n gives as the result nx to the power n minus 1 is true for all cases where n is a whole number and positive. Expanding x plus dx to the power n by the binomial theorem will at once show this. But the question whether it is true for cases where n has negative or fractional values requires further consideration. Case of a negative power, let y equal to x to the power negative 2, then proceed as before. Y plus dy is equal to x plus dx to the power negative 2, which is equal to x to the power negative 2 times 1 plus dx over x to the power negative 2. Expanding this by the binomial theorem, we get x to the power negative 2 times 1 minus 2 dx over x plus 2 times 2 plus 1 over 1 times 2 times dx over x squared minus etc., which is equal to x to the power negative 2 minus 2x to the power negative 3 times dx plus 3x to the power negative 4 times dx squared minus 4x to the power negative 5 times dx cubed plus etc. So, neglecting the small quantities of higher orders of smallness, we have y plus dy is equal to x to the power negative 2 minus 2x to the power negative 3 times dx. Subtracting the original y is equal to x to the power negative 2, we find dy is equal to negative 2x to the power negative 3 times dx. dy by dx is therefore equal to negative 2x to the power negative 3. And this is still in accordance with the rule inferred above. Case of a fractional power. Let y equal to x to the power half. Then as before, y plus dy is equal to x plus dx to the power half, which is equal to x to the power half times 1 plus dx over x to the power half, which is equal to the square root of x plus half dx over the square root of x minus 1 over 8 times dx squared over x times the square root of x plus terms with higher powers of dx. Subtracting the original y is equal to x to the power half and neglecting higher powers, we have left dy is equal to half dx over the square root of x, which is equal to half x to the power negative half times dx, and dy over dx is equal to half x to the power negative half, agreeing with the general rule. Summary. Let us see how far we have got. We have arrived at the following rule. To differentiate x to the power n, multiply by the power and reduce the power by 1, so giving us nx to the power n minus 1 as the result. Exercises. Answers shall be displayed in 10 seconds.